All right, thanks, Matt, for that introduction. Can everyone hear me in the back? Yeah. All right, hope you're enjoying your Sunday here. So today I'm going to talk to you about the idea of being carbon neutral as well as what a hydrogen economy is. Before I get into that, a little bit about myself. So I grew up in the area, in the Northeast. This map is too large to describe my life. So here we are today in New Haven, Connecticut. I grew up about 20 minutes away from here in Milford, Connecticut. Does anyone know anyone from Milford in this area? Nice. So I went to Jonathan Law High School. So there I loved math and chemistry. So then I continued my education about an hour and a half away at Marist College up in Poughkeepsie, New York. I started out as a math major, and then I eventually realized how much I enjoyed chemistry, so I added that chemistry major. So then I realized throughout my time at Marist, I wanted to continue my education in chemistry, mainly in energy science. So that brought me back here close to home at Yale University, where, as Matt said, I'm a second-year PhD student in the chemistry department studying solar materials. So before I get into the meat of the talk, we're going to talk a little bit about some chemistry. So many of you may have heard of, we consider atoms to be, they make up everything. They're the building blocks of life. So atoms can be of different elements. There's a bunch of different elements. Here are just 3 examples. So oxygen, carbon, and hydrogen. They're throughout many molecules in the world, in our life. So us chemists, we like to represent these as spheres. So in this talk, whenever you see a red sphere, that's going to be an oxygen. Whenever you see a gray or a black sphere, that'll be a carbon. Whenever you see a white sphere, that's a hydrogen atom. So atoms then combine to form molecules. So here's an example of 3 molecules. So H2O, does anyone just yell out what's H2O? Water. CO2, does anyone know what that is? Carbon dioxide. Does anyone know what CH4 is? I might have heard methane, so that's methane. So if we look at what these look like, so here we have our 1 red sphere, our 2 white spheres for the 2 H's and the 1 O. We have our 1 gray sphere for the carbon and the 2 red spheres for the oxygen. And then here we have our 1 black sphere for the carbon and the 4 white spheres for the oxygen. Another important concept in chemistry are reactions. So in a reaction, we have what are called our reactants, which is just what we start with. They do some sort of change, maybe like an explosion, to form what we really want, which is our products. So here's an example of a chemical reaction. So we said this is water, so we have 6 H2O plus 6 CO2 gives this 6 H12O6, which is called glucose, which is just a sugar, and then 6 O2, which is oxygen gas. So this reaction might be familiar to some people. This is photosynthesis. This is what plants do every day to get their food in this sugar form. One key thing we want to look at is these numbers in front of all of these different compounds. So here we have a 6, a 1, and a 6. So the 1 is implied. So what this means is we're going to have 6 water molecules. They're going to combine with 6 CO2 molecules to give us 1 sugar molecule and 6 oxygen molecules. So we want to keep in mind what these numbers mean going through this presentation. So now getting into the problem with carbon right now. So this is a graph of the past 800,000 years of carbon dioxide in the atmosphere. So we can see it kind of jumps around a lot throughout this time, but it always kind of stays in this area. The problem, except for current day. Current day, we have this huge jump. So let's zoom in on that plot to the last 300 years, and we can see this light blue curve here is the amount of CO2 in the atmosphere, and right around 1850 is when we see this large jump. So one thing that comes from is that's around the time of the Industrial Revolution. That's when we started digging up fossil fuels and using those to burn to create our energy. So like here's a picture of the time of the Industrial Revolution where we have all these smokestacks, and that's creating CO2 by burning fossil fuels in combustion engines. So what are some problems with this? So if we look at the global temperature, so this is that same plot I showed in the previous 2 slides, except now zoomed in to the past 50 years. And here is the average temperature of the Earth throughout that same time. So if we look, they're kind of both increasing at the same time. So the question is this increase causing this increase in global temperature? And the short answer is yes, so let's go see why that's true. So here we have here's some buildings at Yale, so here's just our Earth, and here's our CO2 in the atmosphere. So what happens is we get our energy from the sun. The sun's going to give off some light, and the CO2 molecules can do one of two things. It can reflect it back away from the Earth, or it can let it through into our atmosphere, and then we get our heat, and we get, use that for energy and stuff. So then once we use it, or it gets reflected, it goes back to the atmosphere, where the CO2 molecules can let it go through again, or again, let it reflect into the Earth. So the problem is when you get more and more CO2 into the atmosphere, more and more of these beams, or these light beams, are going to stay in the Earth and making it hotter and hotter. It's basically like having a blanket around the Earth. So once you put a blanket on, it gets warmer and warmer because it's just recycling that heat. So this isn't only a bad thing for global temperature, it also hurts our oceans. So if we have that CO2 in the atmosphere and you add more CO2, what happens is some of it will dissolve into the water. But it doesn't stay as CO2 in the water. Rather, it reacts with water to form carbonic acid. So many of you probably have heard the term acid before. So acid, we kind of think like maybe hydrochloric acid. We think those are dangerous chemicals, which is usually true. So when you add more of this to the ocean, it's going to make the fish very sad. The fish and all the other aquatic life are not going to be happy by this change in their environment. So where does all this CO2 come from? So like I said earlier, it comes from when we started burning fossil fuels. So one component of fossil fuels, and specifically gasoline, is called butane. So that's this first compound. And when we do a combustion reaction, so all of your engines, what they'll do is they'll take this fossil fuel, react it with oxygen from the atmosphere, and it'll create water and carbon dioxide. So whenever you see these power plants and the exhaust coming from your cars, that's all that water and carbon dioxide. So like I said when I was talking about chemical reactions, we want to look at these numbers. So for every 2 of these butane molecules, we're making 8 carbon dioxide molecules. So we're making a lot of CO2 in this atmosphere, which is just increasing the concentration, which is, as we showed in the previous slides, not a good thing for the environment. So how can we combat this? How can we fight this? So one way is to become carbon neutral. So to become carbon neutral, you take the CO2 that's already in the atmosphere, you do some chemistry called reduction chemistry, and reduce it to make these other fuels. So for example, this is methane. So just keep a simple example. So then you take that fuel, in this case methane, react it with the oxygen from the atmosphere, and do a combustion reaction. And so you get that water and the CO2 again. So you might think to yourselves, but you're still creating CO2. How is this helping? It's okay because this carbon has come from CO2 that's already in the atmosphere. So we're not making any new carbon dioxide. So we're helping the Earth with that. Another way to fight this is to, rather than use fossil fuels, we use hydrogen gas as a fuel. So we take hydrogen gas, react it with the oxygen gas, and we form just water. So this is a good thing here because we're not making any CO2. There's no CO2 being formed in this reaction, and we don't have to worry about that. How can we make hydrogen gas? So my lab, we look at something called a water-splitting photoelectrochemical cell. So let's kind of think about what this means. So water splitting means you're breaking apart water into hydrogen and oxygen. The term photo just means we're using the sun to do this. So we're going to take the light from the sun to do this reaction. Electro just means we're using electricity. So just flowing electrons. And chemical means we're doing some sort of chemistry to do this. So looking at, this is a diagram of what one of these looks like. So this blue area is our water, and this stuff right here is called a semiconductor. So that's what actually is going to take in the light from the sun to make our hydrogen gas. So like we said, the word photo, we need that sun to come in. It's going to give some light to one of these E- are electrons. So when an electron gets light from the sun, it has a lot of energy, so it wants to jump. So like if you think about, if you eat a lot of sugar, you have a lot of energy, you kind of want to run around. So the electron wants to do that same thing, so it's going to go up to some higher state. And then what we leave behind is called a hole. So a hole is just a lack of an electron. But to do water splitting, you need 4 holes. So we're going to have to make 4 of these electrons jump and make those 4 holes. So then the water is going to come in, give up some of its electrons to fill in those holes, and do what's called the oxygen evolution reaction. It'll fill in the holes like so. And then this will the water will become oxygen gas and these H plus ions, which we just call protons. So the O2 gas is going to flow out of the system into the atmosphere, and then these H pluses are just going to float around in solution. They're going to meet the other side of the cell, and at the same time, the electrons are going to flow to the other side of the cell. And then you're going to do what's called the hydrogen evolution reaction. So this is where we actually make that hydrogen gas, like so, and then we can just have something ready to collect that hydrogen gas. So now we have hydrogen gas that we can use for many different things. So let's break apart how we can do these things. So there's the water oxidation side, which I was talking about. So that's this reaction. So we can use molecular catalysts to do this. So that's where the chemistry comes in. So these are kind of large compounds, but we want to focus in on these metal centers. So this IR, this RU, and these IR. So IR is iridium, RU is ruthenium. The problem, you may have not heard of these metals because these are earth rare metals. So one way we can measure how earth rare it is its price per pound. So the more expensive it is, the more earth rare it is. So if we look at ruthenium, that's about $1,400 per pound, where iridium is $14,000 per pound. So just for comparison, if we look at something like silver, which we think is expensive, that's only $200 per pound. So what we want to move forward to is looking at catalysts that use earth abundant metals, something like a copper, because copper only costs about $3 per pound, or something like a manganese, which only costs less than $1 per pound. So this is where we want to move towards, so we can actually make a large scale of these catalysts to make hydrogen gas. So this is something that anyone in this room, this is research going on right now that people are currently working on. So the other side of the cell is the hydrogen evolution reaction, where you actually make that H2 gas. So Josh will talk a little bit more about this, other ways to make it. I will introduce a 2D material called carbon nitride. So it's kind of like the graphite in your pencil. It's just, your graphite in your pencil is just a bunch of carbon things, and that's why it's so easy to write with. This is a bunch of carbon and nitrogen that kind of just stack on top of each other. So that's one way to make your hydrogen gas. So what then can we use this hydrogen gas for? So one thing is hydrogen fuel cell cars. So Toyota makes one, Honda makes one. The question is, why doesn't everyone have one of these hydrogen fuel cell cars right now? There's a few factors, one of them being this costs $60,000, which is a lot for a car. So you'd have to really break the bank to get this car. The other one is hydrogen fueling stations. So this is a map of all the hydrogen fueling stations in the US. We can see there's a lot in California, but not so much up here in the Northeast. But there is some positive takeaway from this map. So if we look at the yellow things, all of these yellow dots are ones that are in development. So we see more and more of these being developed, which means we're going more towards hydrogen as a fuel to reduce CO2 emissions. So if we go back here, there is one in Connecticut. I think it's up in Wallingford. We can see here that it's really not ready to accommodate everyone in the state of Connecticut having a hydrogen fuel cell car. But hopefully we can see more and more of these pop out throughout the US. So just kind of summarizing what the hydrogen economy, state of a hydrogen economy is right now. So right now it's about $5.60 per gallon, which is about the double the price of gasoline. So it's not great right now. It's hard to transport people. That's another research project that people are looking at trying to figure out how to transport it. And we'd have to change our entire infrastructure. Right now it's geared all towards fossil fuels like natural gas and gasoline, oil. So we need to change everything. But with that, we want to look, everyone in this room can work on these projects so we can work towards a future where we're using hydrogen as a fuel and have no CO2 emissions. So with that, I would like to thank you for your attention, and I will be more than happy to take any questions.
Anyone have questions?
Questions for Matt. You get to talk into a microphone if you ask a question.
Is that why ethanol fuel costs so much in different types of cars that use it? Because I saw on a video that it's safer for the environment, but it only is used for certain types of cars because it's limited in some countries and states.
So your question was about ethanol as a fuel? Right, so the reason it's probably expensive in those is that they're making the ethanol from CO2 from the atmosphere. So that's one way you can, so the example I gave about carbon neutral just had kind of methane because it was a simple one, but we can use other fuels like ethanol. But if we take, right now it's hard to do that chemistry to go from CO2 to ethanol. So it would be much more expensive to use ethanol than these fossil fuels we can get from the earth.
How many miles to the gallon does the hydrogen car get?
I think, yeah, well, I looked it up. I think it's about 70, so I guess it does start to work out, but I'm not sure people kind of consider that when they're purchasing their gasoline.
Anyone else?
If cars and emissions give off higher levels of carbon dioxide, right? And that feeds plants and like in the process of photosynthesis. So greenhouse gases, so to speak, how is it that it's bad for the environment if plants feed on carbon dioxide in order to produce, chemical process?
Right, so before we started burning fossil fuels, there was some state where the plant was taking in CO2 and like animals were creating CO2. And that's the level it stayed at, which is that first plot. That's why it's always jumped, because just fluctuations in Earth. But now that we're basically producing CO2 much more quickly than the plants can take in the CO2. So that's what's making it dangerous. And it's just creating like all those problems that I said. Josie?
So I remember reading about the Toyota car when they first released it or something. And one of the major concerns was like how safe the actual engine was, because wasn't it under the passenger seat? And there was a lot of like issues raised about how safe it was and whether it was a good idea to use. So
yeah, so that's definitely a problem with hydrogen fuel cell cars right now, is that you're storing hydrogen gas in your car, which is it's hard to compress it, where like, gasoline is pretty easy to compress. So that's something that's a big research topic that's being done right now, figuring out how we can make these fuel cell cars much safer than they currently are.
So is it dangerous if you went to a car accident with a hydrogen car?
Yeah, that would be dangerous. But it's dangerous to get in a car accident, period. But the hydrogen would not help. That I don't know. I guess it depends on how the car is built.
Are the hydrogen fuel cars better for the environment than electric cars?
It depends, right? So it depends how the electricity for your electric car is being made. Because if the electricity from your electric car is coming from fossil fuels, even though your car is not creating the CO2 emissions, it's creating it elsewhere. Where if the energy or the electricity that you're getting maybe it's like from wind or solar, then in that case, it's basically the same.
How do the hydrogen stations access the hydrogen?
So there's many different, I didn't go into this, but there's different ways to produce hydrogen. I just showed us the one using solar light. The one I believe in Wallingford also uses solar electricity to kind of break apart, do the water splitting, so break apart water into hydrogen and oxygen, and it can capture that hydrogen using electricity.
A follow-up on the electricity comparison. So if I remember correctly, the photovoltaics is about like maybe 4 or 5%, right, efficiency. And you work on, I guess you consume electricity, produce hydrogen as well. What would be the efficiency of that process compared to photovoltaics?
I actually don't know the answer to that question.
I think can I try to
Sure.
hop in? Okay. I think from like the current technology, currently like commercial solar cells are
at a higher efficiency right now than any of these water splitting devices we have. But that's why Matt and I are working on it, I guess.
All right.
If we could